Hey everybody, I just want to kind of go over quickly with you a unique thing about KSP values compared to other Ks. So if I'm talking about a Ka value for an acid and I see a Ka value that has 1 times 10 to the negative third and a Ka value that's 1 times 10 to the third, I can definitively say that the Ka with 1 times 10 to the third has turned more into product than the Ka with 1 times 10 to the negative third. Ks are a ratio of products over reactants. And so if I have a big K, it means I just got more product, right? And that is true in most situations. But when we're talking about KSP values, the coefficients that show up in our equations because of the way that the salts break apart cause problems with that. And you will get in KSP values sometimes hugely negative exponents like negative 20th, negative 30th. But just because it has a large negative exponent doesn't mean that it is less soluble than something that has a bigger exponent. And it's kind of annoying, but you got to do a little bit of work with it. So here is the example I want to work through with you. And I'm not going to necessarily go through like working each of the problems, but I'm going to give you the steps to kind of explain it. So if I compare these 4 different insoluble compounds, silver chloride, lead fluoride, aluminum hydroxide, and strontium phosphate, and you look at these K values here right away to begin with, you would probably take a look at them and say, I'm guessing that the PbF2 is here, and then the AgCl, and then this guy, and then the aluminum hydroxide. And if you look at them, it is not necessarily a safe comparison to compare the K values with all of these. And so what you have to do is one of 2 things. You can make the comparison of strict size of the K to let you know which is more soluble if they produce the correct number of ions. Otherwise, or not the correct number, but the same number of ions, or you have to find the X, the solubility, and then compare them. Otherwise, we can't say that that's an accurate judgment at all. So we are going to take a look at these and see what the heck happens with them. So when I take a look at them, AgCl breaks up into Ag plus and Cl minus as its ions. And when its ice table is set up, it's going to be X and X for its equilibrium value. So when I put that into the equilibrium expression, I'm going to get X squared equaling my KSP value. In the case of lead fluoride, it's going to turn into, like we saw in the example, Pb plus 2 and F minus, but I get 2 F minuses. So in my expression, I'm going to square it. And then when I put in my E values for my ice table, I'm going to put in X for the lead and 2X for my F minus and square it. And that's going to get me 4X to the third, just like I showed you in the example. Okay. With aluminum hydroxide, it breaks up into the aluminum plus 3 ion and then OH minus, but it breaks into 3 OH minuses. So in my equilibrium expression, it's going to be Al plus 3 times OH minus to the third power. That, when we put it into our equilibrium expression, is going to be X times 3X from our ice table cubed. So think about how your ice table breaks down. The 3X would be for the hydroxide. And so when I put all this together and I cube 3, I get 27. So I get 27x to the 4th equaling 1.9 times 10 to the negative 33rd. Then, if I take a look at the strontium phosphate here, I have Sr2 plus ions, and they make 3 of them. And then I have the PO4 ion, and I get 2 of those. So when I set up my equilibrium expression, I've got to have a cubed value for my strontium ion and a 2 exponent here for my phosphate. When I put that into my equilibrium expression, I get 3x cubed times 2x squared, which gives me 108x to the 5th. So in the previous video where I told you these are things that show up time and time again, it's because you can only break into so many different ionic ratios. 2 ions, 3 ions, 4, and 5. And so you pretty much see all of these most of the time here. So you'll see x squared, 4x cubed, 27x to the 4th, and 108x to the 5th. And when you go through and you do the math on those, I get X for AgCl to be 1.34 times 10 to the negative fifth. The lead fluoride is 2.17 times 10 to the negative third. The aluminum hydroxide is 2.93 times 10 to the negative ninth. And the strontium phosphate is 1.3 times 10 to the negative sixth. So when I go and I look at all of those, with this being an exponent of the negative 28th, you would think that the strontium phosphate solubility would not be very close to the silver chlorides, but it actually is. It is a little bit less soluble in this case, but they are close. These guys here are dramatically different in terms of their solubilities because this one makes 3 ions and this one only makes 2. Same thing here. The aluminum hydroxide, its exponent's -9. Strontium phosphates is -6. So it's not an apples to apples comparison if you have things that don't make different numbers or that don't make the same number of ions. So if I was comparing, let's say, silver chloride, silver fluoride, silver whatever, then it would be really easy to do. But if I'm going to see if I got this table here. But if I'm not comparing things that make the same number of ions, I need to do this calculation. So in this case, I can confirm that lead fluoride is my most soluble, silver chloride is next, then it's strontium phosphate, and then it's aluminum hydroxide. So what I was saying about the my list here that I have, and I thought I would show it to you guys. So if we take a look here, if you see how I have barium fluoride, magnesium fluoride, strontium, and calcium, and I look at my KSP values, all of these I can compare right away. And I can automatically say that the barium fluoride is the most soluble because it's got the biggest KSP value. And then in this case, the magnesium fluoride is the least soluble because it has the lowest KSP value. And it's kind of weird to think about. You got to remember the negative exponent is the smaller number. So the more negative it is, the smaller it is. But in the case of, let's say, these chlorides here, when I look at them, I cannot tell you that lead chloride here is the most soluble because I can't compare it to copper chloride because they don't make the same number of ions. So this one makes 3 ions. This guy here makes 2. So what you need to do is you need to figure out your X value of each of these, and then we can compare them. Okay, so that's just something that's kind of unique with these. You would have to do a comparison calculation, find your X, and then the bigger X value would give you your more soluble compound. Okay, so if you have any questions, let me know. Otherwise, good luck.